Hello, my name is Brendan Alvey, and I'm a PhD student at the University of Missouri, and I work under Dr. Anderson in the Mindful Lab. So today I'm going to be presenting this paper for the ICCV WAMMI workshop. The paper is Simulated Photorealistic Deep Learning Framework and Workflows to Accelerate Computer Vision and Unnamed Aerial Vehicle Research. So that's kind of a wordy thing. What we're going to be doing here is talking about how to use the Unreal Engine to create simulated data, which can facilitate your research in computer vision, specifically with aerial vehicles here. So in a nutshell, basically deep learning is the state of the art right now in computer vision. And in the real world, there's a lot of really poor or really no ground truth for a lot of the things that we would probably want. And really there's a low sort of variety in the ground truth that we have, right? And it takes a lot of time and money to get that, basically. So through simulation, hopefully we can get that a lot easier. Also through simulation, maybe we can test where our algorithms sort of break. And really what's driving today's talk is this convergence of the latest kind of computing hardware with kind of where photorealistic simulation is at with these open source tools like Unreal Engine. And so today we're going to be presenting this workflow, or really a couple of workflows to collect an aerial data set in Unreal Engine or AirSim. And we've got some tutorial videos uploaded here to this bit.ly link. We've also got our code and the text tutorials that go along with that up here on GitHub. So in the Epic Marketplace, there's tons of great content. We've got photorealistic data, environments, and models. And the latest version of Unreal has Lumen and Nanite, which allows for some really high fidelity renderings. We have global illumination and extremely detailed models. The really nice thing here about using simulation is that we can get this accurate ground truth really quickly. That goes along with the data. So we can do this offline and just save out images. We can do it online and kind of have an interactive approach. We can save the data out and use it to reconstruct 3D reconstructions if we save out the camera intrinsics and extrinsics. We can also use it to explore. We can look around and use and try different autonomy algorithms and sort of multi-criteria decision-making algorithms, things that explore a space but take into account different factors. We can use this for semantic segmentation, where we can automatically label things, label objects in a scene. We can label them. We can also get ground truth, really, for all different types of things that you might imagine in a scene. Since it's all simulated, we can just kind of obtain that information. So Unreal Engine has been used for all kinds of things. It's been used for games like Fortnite and all kinds of stuff. You can look in the Epic Marketplace. Film, I know The Mandalorian has been using it for their backgrounds. Architecture, I know they use them to model buildings with realistic shadows and a little bit of physics in there. We've been using AirSim, which is a plugin that allows us to get depth, labels, and RGB really easily. It allows us to do sort of validation of the underlying platform physics, so we can try kind of like a little model of autonomy on a simulated drone before doing it in the real world. And this plugin actually came out of a project that was looking at drone racing, actually. So it was trying to fly around and improve drone racing. So it's trying all these different environments that were sort of randomized and changed in textures or changed, objects or their placement and orientation. So I'm going to go over a few use cases. This is kind of what we've been using it for, and maybe what you guys might want to use it for. And really, we're going to try to answer the question of, is it good enough to help with AI and machine learning here? And we think it is, but we're going to try to make that case here. So one of the things that we've used it for is passive ranging. Passive ranging is where typically with sort of depth, when you're trying to predict depth from color images or images, you're using stereo or sort of quasi-stereo, where you have a moving platform and you're looking at sequences of images. With passive ranging, you're looking at only a single image and you're trying to predict what sort of how far everything is in the scene from relative to the camera, without any kind of other context, just that single image. And so with simulation, we're able to get depth at range. This is really hard to get in the real world. It's hard to get depth really far away, dense depth at least really far away. We can use LiDAR to get pretty accurate depth, but it's usually not dense. And there of course could be errors with that. And there's also like very few data sets. I know there's a kitty and a few others out there, but there's not too many out there that have really good depth in the real world. And so there's also these questions like, how do we score and test these models when we have such limited data sets, right? So this is like one experiment we ran. On the left, we have sort of a training set, and on the right, this is sort of an evaluation or testing set. This is from the kitty set. We're going to, on here, we've trained on the kitty set, and we've tested on the kitty set, just in a different place. You can see that, we don't really pick up the real rails and the curb here. We have, the clouds get picked up as like sort of a tree or something that's up close, just a few errors. This is when we train only on a on a limited simulated data set, then it kind of does worse. So like a lot of this stuff just gets picked up as sort of infinite, or at the background here, we're losing a lot of the detail. But when we combine the two, we do kind of better than either of the individual. We're able to get a little bit of that rail in there. Okay, so then we've also been able to use this for explosive hazard detection. We've been able to output grayscale images and pretty photorealistic placements of explosive hazards in scenes. We've been able to put them into a benign background, extract their templates along with their alpha masks, and insert them into real backgrounds. So we can take sort of a simulated template, put it into real backgrounds, and use that almost as a form of augmentation, where we can come up with a lot of variety in images here. And these are the results that go along with that, with the explosive hazard stuff. So really the findings here is just that sim helps a lot. If we're using, really we found that doing that, what I just described, where you take that simulated object and you insert it in the real background, that turned out to be pretty helpful here. And then really the combination of that along with sort of simulated data, full sim, and some real data did the best than any of them individually. And we were able to really improve detection results from a limited data set. We've also been able to do some experiments with rapid prototyping. This is a really good use case of I think, this sort of simulation and AirSim and everything. We did a thing with contextual fusion where we trained basically 3 different classifiers or 3 different models under different contexts, so different times of day. And then when we at detection time, we're able to evaluate sort of which context we think we're in, or to what degree we're in which context, and then fuse accordingly. And we're able to show some good detection results with that. So then we can also do some spatial relation things with this. We've been able to explore like how you could use sort of fuzzy relations to make sort of fuzzy queries. So you might want to say sort of what's near me. Say you have some little object here and you want to ask what's near it, and objects sort of have a fuzzy membership to a place, since they're don't exist in one particular area. So you can get sort of partial memberships and everything like that. We've also been able to look at virtual reality and how we might be able to, and how we can use Unreal Engine, take some images, project them into 3D, and then create this sort of environment that we can walk around in and actually sort of explore in augmented reality. So here's our big framework here. We've got our 3D content that's coming in from Unreal or our user modeled content, and all of that is going into our modeled scene here. We've got environment properties and lighting. We've got a different sequence editor, and our cinematic camera that we throw in that we can use with the sequence editor to create keyframes, which get interpolated to output data to create essentially a data collection plan here. We have our custom shaders that can also be used with the movie render queue to output all sorts of things. We have color, semantic segmentations. We have LiDAR. LiDAR is enabled by the AirSim plugin here. We have the LiDAR, or along with the AirSim plugin, we have all these other different sensors. We could do depth and sort of simulated RGBD. We have all the metadata associated with that. We can sort of explore autonomy and do a sort of scripted flight plan with AirSim, and really all of this interacts with ROS, or we can visualize it with Open3D or OpenVDB. And as we mentioned, we can do some stuff with augmented reality with Unity and the HoloLens. And then our little AirSim package we're calling is PCSim, which kind of does sort of all this at once and packages it all up. So see Drew's tutorial for that. Okay, so we can do a data collection all in Unreal Engine if we want. We can just drop in a little scene camera object, can change different settings about field of view, sensor size, sort of different things like that. We can use a measurement tool if we want to place our camera at a specific height to sort of set a keyframe. And then with the movie renderer queue, we can just press S and sort of create keyframes, and then we'll be automatically interpolating between them, and and then we can collect data sort of smoothly as the camera pans between keyframes. We can also enable custom render passes. We can get things like the object ID out of it. We can get high quality RGB from it. We can get sort of normalized depth. We can get all sorts of different things if you want to if you create custom shaders and hook it up to the custom render passes. In the future, we'll probably have some stuff about how to do blueprints here, where we can sort of script a camera to move around, do all this collection, and sort of interact with the environment a little more like AirSim does, but natively in Unreal, and also supported in Unreal 5. Okay, so then in AirSim here, like I mentioned, is just this Python client. It's really great. It does skip some of the rendering pipeline a little bit, so you don't get quite as high fidelity. You also don't have all the camera simulation sort of things, but you can get sort of the depth, the segmentation, and the color, and that can get you a long way with probably a lot of the different things that you might be exploring. You get the camera intrinsics and extrinsics, and do 3D reconstruction of a scene. So I'm just going to wrap it up here and talk about the summary and our future work here. Hope you enjoyed the talk. The paper and videos. Hope all this stuff is useful for you guys. The tutorials up here on YouTube. We've got also our GitHub again, and really the question, has SIM gotten to the point where we can use it for AI and machine learning? I think we've kind of proven, at least we think we've been able to use it for some stuff, and we think we're in good company here. We've got Google and Tesla and plenty of other big players who are definitely using simulation to improve their machine learning and AI algorithms. So I think it's the way to go. And really, there's countless possibilities here. Tons of different things you can do with it. Really, anything that you can imagine that you could do in simulation, you probably can. It's just imagine a limit of how much work you want to put into it. I think there's a lot of stuff that is pretty low-hanging fruit and that can really help with stuff versus trying to do it the long, hard way in the real world right now. So I'm just going to leave it there, but thank you for listening, and I hope you enjoyed the talk.